Okay. Good afternoon, student. Today we're going to learn application of partial derivative. So one of the application of partial derivative is to find the stationary point. So what is stationary point is either maximum point, minimum point, or saddle point. Okay, so we have a multivariable function 4 minus x squared minus y squared. So from the graph, we will know that there's a maximum point. So what is the uh, actual value for the maximum point for this function? Next graph show that it has a saddle point. So how to find the saddle point for these multivariable functions? So what is saddle point? If we change the view, so we will find out the curve is concave down. If we change from another view, we'll find out the curve is concave up. So from here, we have a saddle point. So with the one independent variable case, the stationary point is either a maximum, minimum, or an inflection point. So we have the same concepts for function of more than one variable. There's a stationary point is either a maximum, minimum, or a saddle point. So how to find stationary point? Stationary point will occur when the first order partial derivative del f over the s equal to 0 and del f over del y equal to 0. So there are three types of stationary point. It's either maximum, minimum, and center point. We can decide what type of a stationary point we have using the second derivative test. So procedure to find stationary point for function of several variables. Step 1 is find the first order partial derivative del f over del s and del f over del y. Second step is we let the first order partial derivative equals to 0 for del f over del s and also del f over del y equal to 0. And we solve the simultaneous equation to find the value of s and y. So step 3, we have to find the second order partial derivative, del square f over del x square, and also del square f over del y square, and the mixed second order partial derivative, del square f over del s del y. Finally, we're going to using the second derivative test to determine whether the stationary point is maximum, minimum, or saddle point. So from the second derivative test, we have the case 1. If the discriminant, this is a formula for discriminant, del square f over the x square multiplied by the x square over the y square minus the mixed second order derivatives you square. If we get greater than 0, that means positive, and we have to check also the square f over the x square also positive, so we can make the conclusion the stationary point is a minimum point. Case 2, if the discriminant is positive, but the second order partial derivative del square f over the x square less than 0 means negative, so we can make the conclusion the stationary point is a maximum point. Case 3, if the discriminant is negative, then the stationary point is a saddle point. Finally, for the case 3, if the discriminant equals to 0, so we cannot make any conclusion to determine whether this secondary stationary point is maximum, minimum. That means this second derivative test is failed to make conclusion. So next, we're going to look at one example how to determine stationary point is either maximum, minimum, or saddle point. Before that, we're going to look at the conclusion. That means if positive would be the minimum point, if positive negative would be maximum point, And for the case 3, if your center point is negative, okay, and also if we get 0, that means no conclusion. So for this example, we're going to find the maximum and minimum value for this multivariable function. So how to find the maximum, okay, or the minimum value? So step 1, we're going to find the first order partial derivative, okay. So we have to differentiate respect to s, so we know that the first term is 2x squared. When we differentiate, we get 4x. And I hope you can recall back to this lecture is already the third lecture already. So our first lecture is the introduction of partiality. You have to recall back how to find first order partial derivative. Okay. We have to find also del f over del y. Okay, so first term, we differentiate respect to y. So first term is a constant. We don't get any variable y, so it's a constant, so it will be 0. Second term, when we differentiate respect to y, so we have the x. Okay, so third term also a constant will be 0. So differentiate y squared respect to y will be 2y, and 11y when differentiate respect to y will be negative 11. Okay, step 2, we let the first order partial derivative equal to 0, we get the okay, and we try to rewrite, we get the equation 1. And we let also the first order del f over del y equal to 0. We try to rewrite, we get the second equation. So we have to solve the symmetric equation 1 and equation 2. So I multiply the equation 2 by 4 because I would like to eliminate variable x. So we have the 4x plus 8y equals to 44. We get equation 3. Okay, so we have the equation 1. Then we minus equation 3 and this equation 1. So we can eliminate the variable x. So we have 7y equals to 28. So finally we get y equal to 4. We substitute into the equation 2. Then from the equation 2, we substitute value y equal to 4. Then we get x equals to 11 minus 8. We get 3. So then we get value s is 3, y is 4. So next question, we have to determine whether this value s equal to 3, y equal to 4 will give the function maximum value or the minimum value. So how? We have to go to the step 3, find the second order partial derivative. So from the first order partial derivative, we have to differentiate again respect to x. We get 4 cos 4x. Differentiate respect to x, we get 4. Y is a constant, so differentiate constant, and 16 also constant becomes 0. And then from the first order, the f over del y, we differentiate again respect to y. So first term is x is a constant, so differentiate to y, we get 2. Third term constant is 11, 0. And then we find the mid second order partial derivative, the square f over the s del y, get 1. So finally, we go to using the second derivative test. So from the discriminant formula, we substitute our second order partial derivative and we calculate, we get positive, and we have to check again the del square f over the s square, we get also positive. So conclusion, we get a minimum point. So s equal to y and y equal to 4, it will give the function f minimum, where the minimum value, okay, of the function will be, we substitute value s and y, and then we calculate, finally we get negative 46 will be the minimum value. So from the graph of the multivariable function, you can see that there's a minimum point with the coordinate x3 and then the coordinate y4. So I think that's all for today's lecture. So I will share with you all next example with more application of partial derivative for the next class. Okay, that's all. Thank you for your attention.